Welcome to numerical ship and offshore hydrodynamic course. Today is the lecture 10 and today we are going to discuss, we are continuing to discussing the basic hydrodynamics. Okay. And this is the keyword that we are going to get to find out this lecture. Now, in last class we have discussed about the boundary value problem that we are going to establish using the Laplace equation and some boundary conditions, and from there how I get the pressure. Now, let us take for a simple problem the solution also very simple. Okay. So, let us try one solution. Now, let us try to solve this Laplace equation okay, with this boundary conditions. You can see that here the boundary conditions are not very complicated, right. Now, let us take this is your rectangular domain and this is your boundary conditions and your governing equation is basically the Laplace equation, that is we are going to solve. Now, how to attack this problem? Okay. So, let us see. For this sort of problem many analytic solution exist. Okay. Now, assume that your phi is this is called the separation of variable. This phi is function of x and y, is a two dimensional problem, and I separate this solution in x which is only the function of x and then y is the only the function of y. Now, if you substitute this in Laplace equation, then this will get this x double dash into y plus y double dash into x. Now, if I rearrange this, then we can get that x double dash by x y minus y double dash y by y equal to minus k square. Now, here the tricky part is it should be plus k square or minus k square. To see that, if I go back here, I can see that horizontal direction is my x and then vertical direction is my y. So, I really do not need the sinusoidal solution in the direction of y. So, therefore, that is how I can fix my k, so it is minus k square y. So, that you can get here two ordinary differential equation, one is x square plus k square x equal to 0 and second one is y square minus k square y equal to 0. Now, here it is very well known that solution is basically a solution for this problem is harmonic and it is parabolic, right. So, I can write the solution for x is c1 cos k x plus c2 sin k x and direction of y is d1 cos hyperbolic k x plus d2 sin hyperbolic k x. So, now, why it is, that is why I say that this taking the k is typically based on the fact that I need the sinusoidal solution in the direction of x and I need that other solution in the direction of y, because wave is not created in direction of y, it is only propagating in the horizontal direction, right. And then you know that your solution is very simple, phi x y equal to x x into y y. So, now you substitute everything in this equation. So, this is basically your solution. Now, this C 1, C 2, D 1, D 2 is your constant and you have to find out this constant from your boundary conditions, right. So, what we get overall? Now, as long as this f x is simple function, the solution of the Laplace equation is easy. However, the solution is extremely difficult if f x is a complicated function. Now, in context of our problem, this f x, I mean it is first of all it is not the f x, it should be f x and t, because the wave is function of time as well as the function of space and this is complicated. So, therefore, such simple solution might not be useful when you solve typically a hydrodynamic problem that ship is moving in ocean and then under the waves condition. Such a simple solution not possible, right. So, that is why although the solution of Laplace equation is not that difficult, you know that you can get it from here, it is simple, this separation of variable will do. However, because of this complex the boundaries, right, typical sheaf hydrodynamics problem is not as simple as solving a Laplace equation with simplified boundary conditions, right. Now, I actually am leaving one homework for you, let us just try to solve this. Next, we are going to move that why I say it is complicated. Okay. Now, try to find out that what is the equation and what is the boundary condition in case of a sheaf hydrodynamics. Now, we have this assumptions that fluid is incompressible, fluid is inviscid, fluid is homogeneous and the fluid is rotational, right. Now, when we assume the fluid is inviscid, then there or the irrotational everything. So, then we can define a velocity potential phi, which is the Laplace equation, right. Okay. So, this Laplace equation we are going to take our governing equation. It is simple, because in the last class also we have discussed the same, here also we are discussing the same. Now, let us see that what is the boundary condition. Now, you can see this blue region is basically the fluid region, where this del square phi equal to 0 exists, right, the mass conversion. And then let us see the boundaries. You can see here you have this, I just make this boundary as a the black lines, right. Now, let us find out that what are those boundaries. Now, this bottom part you can see bottom, we can call the bottom boundary surface, or here you can apply the bottom boundary conditions. Now, you can see this two part actually you can call a radiation condition apply, because it is you can say it is a far field, because we can assume the ocean, if you look at this horizontal direction, it is infinity. Then what happened to the far field, that is also we need to apply some condition, we call it a radiation condition. And then this we can call this as a non-linear free surface boundary condition. Why? Because I am assuming now this is the boundary of we can call it the free surface, because this is the boundary we are having the air and the water. And here you remember this is the second interesting thing, that actually we are different from any other field. In case of mechanical, we really do not deal with the free surface. In fact, in aerospace also we do not deal with the free surface, only in our case when you do the ship waves interaction, right. In this particular fluid structure interaction, we have to deal with the free surface, which is the surface in the top side is air and the bottom side is water, right. You think that in aerodynamics you really do not have these cases, right. In mechanical you do not have these cases, right. Typically for offshore structure, for civil engineers, they are encountering this problem, and also we are. Now, why I call this a non-linear free surface, because this wave is non-linear in nature, right. However, we can make little bit approximation, and what are the approximation, definitely we are going to discuss in coming classes, and we can approximate this non-linear free surface to the linear free surface boundary condition. That what is this condition, and what is non-linear free surface condition, what is linear free surface condition, definitely we are going to discuss in future classes. And one more very important boundary condition we have not yet discussed, which is called the body boundary condition. Now, what is the body boundary condition? Body boundary condition says that under these waves, when the waves hitting the structure, you can see my initial days, this first class I think I showed that video, when this body start oscillating, and because body start oscillating, there is some kind of waves is generated, and also when the incident wave or the ocean waves hit the structure the structure also start oscillating. Then what are the kinematics is there? What is the condition? So, that condition is known as body boundary condition. Now, you know that condition is very easy, like what is the condition that body remain on the ocean? If you think what is the condition that body cannot leave the ocean? What is the condition? Now, you see here I just show from here that it is the pen and this my hand is with me. Now, suppose if I move my hand up and down, then what is the condition? Then pen also remain here. The condition is the normal velocity of my hand should be equal to the normal velocity of the pen, right. If that velocity is different, then let us see what is happening. Now, let us see the velocity of the pen and velocity of my hand has different velocity, with different normal velocity. Then what happens? Let us say the velocity of normal velocity of the pen is more than the normal velocity of the hand. Then what is happening? Then you can see that my pen is coming out of my hand, right. So, ship really cannot go air, right. It is not like a ping pong ball is going up down. I mean, that is where you are going to play in when you go to the beach, you play with the ball, right. Ship is not like this. So, it means that normal velocity of the water particle associated with the touched with the ship, both are having the same velocity, and that condition is called the body boundary condition. Okay. And finally, we have the initial condition. Initial condition is basically where there is no waves. So, at time t equal to 0, we assume there is no disturbance, then ship is very much happy with in the static condition, then weight is balanced by the buoyancy. So, that condition is called the initial condition. Okay. Now, before I move into the next topic, some geometric understanding, let us try to understand. Okay. Now, if you know that this is the well known when this d phi equal to del phi del s dx plus del phi del y dy plus del phi del dz, like if phi is a perfect differential, then this is the condition. And of course, like from mathematics, if you have studied mathematics little bit, so you can find out that velocity potential is a perfect differential. Okay. Now, if it is so, then what is del phi del n or d phi dn? So, here you can see that it is I can write in this form d phi dn equal to del phi del x into dx dn plus del phi del y into dy dn and del phi del z into dz dn. Now, if it is so, then actually what we could do is I can write this in a vector form. How? Now, you can see that in the next slide, you can see that I can write del phi del x as I del phi del x, because it is a component along the x direction, then j del phi del y and then k del phi del z. So, I can write in vector form, right, because del phi del x is the direction of I, del phi del y is the direction of j and del phi del z is the direction of k. And similarly, I can write the del x del n equal to n x and del y del n equal to n y and del z del n equal to n z. So, that is also I can write in a vector form, n x in the ith component, n y the jth component and then n z is the kth component. So, if it is so, basically that del phi del n is nothing but the grad phi dot n. So, this is also from the vector understanding the vector also we can get this, like velocity or a dot b means what, the component of a along b, right. So, in similar way grad phi dot n is basically the component of the velocity in the normal direction, right. So, now on when I say the component of the velocity in some direction or in the normal direction, normally you are going to use grad phi dot n. So, it is understand that component of the velocity along the direction of n. Okay. So, this is one thing that you have to understand. I mean, I know that you know all these things known to you, but still I just discussed this. Okay. So, that is what I said, the fluid velocity normal to the surface. Next one, suppose some more basic understanding. Suppose a surface phi is a surface x y z equal to 0. Assume that is a surface. In fact, you can add t also over here, that phi x y z t equal to 0. Okay. I mean, in reality that is not the case. Okay. Now, if it is so, then d phi dt equal to, I can again in similar line I can write, it is del phi del x into dx dt plus del phi del y into dy dt plus del phi del z into dz dt, because I know that d phi equal to del phi del x dx plus del phi del y dy plus del phi del z dz, right. So, this one. So, in similar line I am instead of n I just use the d phi dt. Now, again I can write in vector form, vector dot product as follows, like d phi dt equal to I del phi del x plus j del phi del y plus k del phi del y, and then this dx dt I can write as a x dot, dy dt I can write as a y dot, and dz dt I can write as a z dot, right. Now, you see what is this? The left hand side is nothing but the grad phi, and the right hand side is nothing but the velocity, which is r dot. So, I understand that d phi dt is nothing but grad phi dot r dot. So, now r dot is the velocity. So, what is the meaning is that velocity along the tangential direction, right. Now, if you look at the first line, when I say that phi x y z equal to 0, you can write phi x y z t equal to 0. Okay. I mean, phi can be function of t also, and if it is so, then d phi dt definitely going to be 0. So, in the left hand side I called d phi dt equal to 0, right. So, here that d phi dt equal to 0 we know. So, therefore, I can see that grad phi dot r dot equal to 0. Now, you see from the vector what we get from here, it means that gradient grad phi is a vector and r dot is a velocity vector, their dot product is 0. So, therefore, grad phi definitely perpendicular to the r dot, right. So, this is the take. So, I understand that grad phi is perpendicular to the r dot. So, if it is so, we can see here, suppose phi x y z equal to 0, if this is the surface, then definitely I can say that grad phi is perpendicular r dot. So, grad phi is the normal to that surface, and therefore, I can say that the surface normal n can be defined as grad phi divided by modulus of grad phi. Okay. Fine. So, these two geometric understanding if we have, and then we can actually try to find out what is the kinematic body boundary condition, and this is very important concept in our numerical sheaf hydrodynamics. Not numerical sheaf hydrodynamics, this is the if you consider wave dynamics, then also understanding this kinematic boundary condition is very important. Now, here what is we can see here, like this f x y z t is basically the similar to my phi here, phi x y z 0. So, instead of phi I am writing that f x y z t equal to 0. Now, this is basically the surface. So, this basically this surface I can call that equation is f x y z t, fine. And then this surface has a velocity v. Let us assume this surface has a velocity v. Okay. At some point of time here, at some point of time So, this is the direction of the normal n. Now, this white one is nothing but the fluid particle. Now, assume that this fluid particle also having a velocity q. Okay. So, and also this also you can see this q equal to nothing but grad of phi, okay, under this all this condition that we have discussed. Now, what is the condition that this fluid particle will stay here with the in the boundary surface f. So, this question is very clear that what is the condition that this fluid particle stay here. So, this fluid particle is not coming out of this boundary surface f. What is the condition? So, we discussed just right now like that how this pen is taking with my hand. The idea is basically the normal velocity should be of the boundary surface should be equal to the normal velocity of the particles, right. So, this is what actually discussed a few moments back when I say that pen should stick on my hand if the velocity of my hand, the normal velocity of my hand equal to the normal velocity of the pen, right. So, the similar argument here I am just writing this picture over here. So, this is the point P and here you have this q is the velocity of the fluid particle, v is the velocity of the surface. So, therefore, at this particular point the normal velocity of the boundary surface should be equal to the normal velocity of the velocity particle, right. So, this is clear. Now, if it is clear then rest part is basically algebra. Okay. Okay. Just clear this. Yeah. Okay. Now, if this is clear, the remaining part basically the algebra. Now, again before we really try to solve this problem, let us do one more thing. Okay. Now, this is we are writing that f x y z t equal to 0 or just you can write that sake of writing very little bit smartly that x y z we write in terms of r. Okay. Fine. Now, if it is so and then actually I just do a Taylor series expansion. Now, I am just trying to find out what happened with f r plus delta r plus t plus delta t. Okay. Now, here this f of r plus delta r, if I use the Taylor series expansion, it becomes f r t plus delta r into grad of r t plus delta t del f delta. So, this is a very standard, this is very standard, right, this is very standard. Now, here this part goes to 0, right. Now, if this part goes to 0 and then we can write that delta r into grad f equal to minus delta t del f del t. So, then if I divide it the throughout the delta t, so I get delta r by delta t grad f equal to minus del f del t. And if it is so, we can find out that v dot grad f equal to minus del f del t. So, now let us understand this concept. Okay. So, this is something actually we are going to use to find out the kinematic body boundary condition. Now, you see at P as I said v dot n is equal to q dot n, right. So, normal velocity of the boundary surface should be equal to normal velocity of the water particle, and also I know that n is nothing but grad f by modulus of grad f, that is also we know. So, therefore, I can replace v equal to grad f by modulus of grad f equal to q dot grad f by modulus of grad f, right. And then we have V dot grad f equal to Q dot grad f, fine, because this modulus of grad f is nothing but a scalar term and both sides will be cancelled out. Now, from here we are actually using this result, that V dot grad f, actually I am going to replace this V dot grad f. Okay. Why? Let us see that what we get if I do this. Now, once I do that, okay, let me take this somewhere else. Now, here you can see that this V dot grad f now actually I replace by minus del f del t. So, what we achieve by doing this? If I do that, finally, we will get this equation, that del f del t plus Q dot grad f equal to 0 at P, and this is very well known and everybody knows what is this equation, right. This equation is very well known to everybody, and this equation is nothing but the material derivative equal to 0. Now, this is the kinematic body boundary condition. Now, we said if f is the boundary surface, then that water particle should be sticking to that surface if and only if the material derivative df dt equal to 0. Okay. So, with this understanding, let us stop today, okay. And in the next class we are going to discuss the more concept on the hydrodynamics. Thank you very much.